Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this my YouTube channel. In this video, we are going to discuss about the basics, introductions involved in the infrared spectroscopy. In previous video, also we have started with some basics related to the infrared spectroscopy. In this video, we are going to see actual what is the infrared spectrum. Also, we will see what is the theory behind the infrared spectroscopy. Now, if you are coming first time to this my YouTube channel, then you can watch my previous videos, and if you like the content of this channel, then you can subscribe to my YouTube channel, and don't forget to share with your friends. So let's begin with our today's session. What are the learning outcomes of this particular session? After this session, students will be able to explain about which are the wavelength ranges of infrared radiations, explain theory of infrared absorption spectroscopy. Now we will see what is the actual infrared spectrum appears like. Now here I have taken the representative example of ethanol just to explain you how infrared spectrum appears, what are the different regions that are present in the infrared spectrum. So here you can see first thing, infrared spectrum is obtained for any compound by plotting a graph of the percentage transmittance on the y-axis and the wave numbers in the x-axis. In previous video we have discussed in detail why we are going to use the wave numbers. The middle infrared region is ranging from the 4000 centimeter inverse to 400 centimeter inverse. So this is the wave number. Because we have discussed in detail why the wave numbers are used instead of wavelengths, because it is very difficult to remember the wavelengths, because this particular region is having very far infrared spectrum, and due to which wave number is directly proportional to the frequency, and it is expressed in much more convenient numbers, and that's why they are represented in the wave numbers. So here just let me tell you what is the meaning of this. Suppose if we get this particular flat line, now you can see here it is obtained above the 80, means you can consider it as approximately 90. So means the 90% of light is passed as such due to this particular in this particular wave number. Means whatever the wavelength of these radiations is there, these radiations which are having this wavelength is passing as such from our sample. But if you observe this particular number, that is the 3391, the radiations which are having the wave number of 3391, they are absorbed right about at the 40. Means this particular 40% transmittance is there, means 60% of radiations which are having the wave number 3391, they are absorbed, and this absorption is due to the OH. If you see the structure of that particular this ethanol, so many bonds are there. There is the carbon hydrogen, then carbon oxygen, also oxygen hydrogen. These are the various types of the bonds that are present in the particular this ethanol. Also here there is a appearance of another peak, that is the peak at the 2981. This is due to the CH, that is the carbon hydrogen single covalent bond, that is known as the stretching. What is the meaning of stretching? What is the meaning of bending? That we will discuss afterwards. These are known as the modes of vibration. What is the meaning of stretching? As I said, this particular bond is behaving like a spring. So if this particular both the atoms or one of the atom, if they are stretched away from each other, then whatever the transitions that are obtained, these transitions are known as the stretching. Then typically this particular IR spectrum is divided into the two regions. One is the group frequency region, which is ranging from 2.5 micrometer to 8 micrometer, and if we express in terms of the wave numbers, it is expressed from 4000 to approximate 1300 or 1300. This particular region is known as the group frequency region. Generally in this region, for a single molecule or single atom, we will get only single peak like we have obtained like this. But in this region, this second region is known as the fingerprint region, which is more complicated, which ranges from 8 to 15 micrometer and having the wave number of about the 1300 to the 400 centimeter inverse. So in stretching and bending vibrational bands are associated with the specific structural feature or functional groups that are observed in the frequency. For example, here this oxygen and hydrogen stretching, that is the OH stretching, is observed at frequency of about 3391 centimeter inverse, where CH stretching is observed around about the 3000 centimeter inverse. So specific group will show a specific band at the infrared spectrum. Then this region is also known as the bending region, because whatever the peaks that are arose in this particular region, they are due to the bending vibrations that are present in the molecule. So this bend, though we are getting so many peaks in this particular region, some peaks are very characteristic, as you can see over here, around about 1000 to 1100 we are getting the peaks that are due to the CO stretching. Means if a peak is obtained in this particular region, then you can say CO functional group is present in our sample. So this is the typical IR spectrum of the ethanol. Now here you can see whatever the light that is falling on this particular sample, all the light is absorbed because there is no any transmittance. 0% transmittance is there, means 100% absorbance. In this way, this particular peak is observed. Now we will see what is the theory behind the IR spectroscopy. Now, when infrared radiations fall on the molecule, these molecules absorbs the radiations when a bond in the molecule vibrates at the same frequency as the incident radiations. Now we have seen various frequency regions which are ranging from 4000 to 400 centimeter inverse. So whatever these different radiations are there, all these radiations, when they fall on the surface of that particular molecule, and these particular bonds that are present in the molecule, they vibrate only, they will absorb the radiations which are having the same frequency as the incident radiations. After absorbing radiations, these molecules have more energy and vibrate at increased amplitude. As we know that whatever these atoms that are present in the molecule, they are not fixed, they are continuously vibrating. In addition to that, if infrared radiations fall on the surface of that particular these atoms, and if these atoms which are vibrating at certain frequency, and if the incident radiation frequency is same, then these atoms will absorb the radiations and these molecules have the more energy and they vibrate at the increased amplitude. And the frequency absorbed, it depends on the masses of the atoms in the bond, the geometry of the molecule, and the strength of that particular bond, as well as the several other factors. Means suppose carbon-carbon bonded with oxygen will show a different frequency, and carbon-carbon bonded to hydrogen, it will show the different frequency. That's why frequency absorbed, it depends on the masses of the atoms like carbon, oxygen, hydrogen that are present in the bond, the geometry of the molecule, as well as the strength of the bond. not all molecules can absorb the IR radiations. Means those molecules which are diatomic, like for example chlorine, bromine, they does not absorb the infrared radiation. But if a molecule is having, now why this particular atoms does not absorb the infrared radiation? The reason is dipole moment. What is the meaning of dipole moment? The molecule must have change in the dipole moment during the vibration in order to absorb the IR radiations. And the frequency of radiation must be equal to the natural vibrational frequency of the molecule. Those molecules which show dipole moment, they only absorb the infrared radiations. As I said, chlorine, bromine, these diatomic molecules, they does not absorb the IR radiations because they does not show any dipole moment. Now what is the meaning of dipole moment? Now heteronuclear diatomic molecule is composed of two different atoms. Now if we consider a chlorine, both the atoms that are involved in the molecule are same. So there will not be any electronegativity differences there between these particular atoms. As there is no any difference between the electronegativities observed, due to which partial positive and partial negative charge is not generated on these atoms, and due to which these atoms or this molecule does not show any dipole moment. In opposite to that, heteronuclear diatomic molecule is composed of two different atoms. So if these two atoms are different, surely there will be difference in the electronegativities observed. So when such atoms with different electronegativities form a bond, electron density in the bond is not equally distributed. Like in chlorine, electrons are lying exactly at the center, but in case of heterodiatomic molecules, say for example hydrogen fluoride, the electron density is not equally distributed. Now here we can consider the example. In the molecule of hydrogen fluoride, that is the HF, the electron density in the bond shifts away from the H atom towards the more electronegative fluorine atom. So in a single covalent bond, it is always observed that a more electronegative atom will attract the electron pair towards towards itself. So when in the HF single covalent bond, the always electron density is towards the fluorine, because fluorine is more electronegative. Due to which what happens? Partial positive charge is generated on the hydrogen atom and a partial negative charge is generated on the fluorine. And due to this difference in the charges, a electronic dipole is induced in that particular molecule. So such a molecules only show the infrared absorption of infrared radiations. And this bond is said to be a polar when such charges separation exists. Such polar bonds only absorbs the infrared radiations. Then HF molecule is a linear diatomic molecule with one polar bond. Therefore, this molecule is polar and it has a dipole moment. And as it has a dipole moment, it is capable of absorbing the infrared radiations. So this is the basic requirement for absorption of infrared radiation. The dipole moment mu is the product of charge, that is the Q, and the distance between the charges that are present. Here charge is nothing but our atoms, that is the hydrogen as well as the fluorine, because they are having a partial negative and a partial positive charge. So mu is nothing but the Q into R, where mu is represented as a dipole moment and the Q is the magnitude of charges and R is the vector going from negative charge to the positive charge. So this is the theory behind the infrared spectroscopy. Thank you. If you have any queries related to the instrumental methods of analysis, then you can contact me on this particular mail ID. If you like the content of this video, then like, share and subscribe to my YouTube channel. Now in next video, we will see what are the different modes of vibrations in the diatomic as well as the polyatomic molecule. Thank you.